I do think that the deeper idea of reverse engineering kernels is powerful and probably holds across architectures. So the central message isn't really like, here's the particular theorem for fully connected networks. So the central message is, let's think about the inductive bias of architectures in kernel space directly and see if we can do our design work in kernel space instead of in a parameter space.
Hey there, I'm your host, Kan Jun, and we are Generally Intelligent, an independent research lab developing AI agents that mirror the fundamentals of human-like intelligence and that can learn to safely solve problems in the real world. On our podcast, we interview researchers about their behind-the-scenes ideas, opinions, and intuitions that are hard to share in papers and talks. We hope you learn as much as we have in our quest to understand and build the mind. Jamie Simon is a fourth-year Ph.D. student at UC Berkeley, advised by Mike DeWeese, and he's also a research fellow with us at Generally Intelligent. He uses tools from theoretical physics to build fundamental understanding of deep neural networks so that they can be designed from first principles. Welcome, Jamie. We're really excited to have you on the podcast and also just in general.
Excited to be here.
So we always start with, tell us the story of how you developed your initial research interests and how have they evolved over time? I know you started out in quantum computing, so what happened?
I studied physics and mechanical engineering in undergrad. Those two majors chosen with the sort of dual intent of like first understanding how the universe works and then also being able to build things and make things and affect the world around me with those tools. And I ended up exploring a variety of different directions in this broad space of understanding and building. I worked as a data scientist for a time. I did optics. I worked on a robotic sailboat in undergrad and then got into quantum computing when I was a senior. I joined a quantum computing lab at Virginia Tech. I ended up taking a gap year and doing applied experimental quantum research in Sweden, actually, nanofabricating. And when I showed up at Berkeley, I had the expectation that I would continue on this like path towards becoming a quantum mechanic. I had actually told Berkeley that I would do this in my application. I had no notion I would do machine learning at the time. I showed up at Berkeley and two major things happened. Well, actually, one thing happened and one thing didn't. The thing that didn't happen is that I didn't find research at Berkeley in physics that I was really excited to do. I found that as much as I loved learning physics and developing the understanding of its core ideas, the applications seemed too technical and narrow and too far removed from things that were affecting the world around me. And despite some really interesting choices for labs in the physics program, none of them seemed exciting enough to me. And the other thing that did happen is I moved in with one of my high school best friends who happened to be a Ph.D. student at Berkeley studying machine learning from a practical perspective. And early on in the first few months of my PhD, we had a conversation that went like, yo, Jamie, do you know that no one understands how neural nets work? If you could figure it out, it would be hype. I was sold.
It would be hyped.
And he was right. It would be hype. The thing that really appealed to me about this was the fact that I love to build first principles understanding of things that are confusing. I think the intellectual challenge that's the most appealing to me, and the thing I've always felt like I always sort of have the comparative advantage in, isn't the hardcore computation. It isn't the application of principles. It's like starting with a system that's doing something weird, with the challenge being like, how do we even think about what this is doing? That's exactly the challenge that machine learning presents today.
Mm-hmm. When you first started studying deep learning, what felt interesting to you?
The things that felt interesting were just the core idea that this incredibly simple learning algorithm, just initializing some random function and taking the simplest possible set of optimization steps. The fact that this learns such non-trivial, rich, interesting things, despite the naivety of the setup, was, I think, the main, and still is the main thing I'm intrigued by and I'm trying to understand. The fact that the ingredients are so simple to a physicist feels like there ought to be a simple understanding to go along with it. And I guess to flesh that out a bit more, I came from a background of condensed matter physics, which is sort of the quantum physics of materials and, crystals and solids and glasses and stuff. And I recall that in my first year, I felt sort of a strong analogy between a material whose internal degrees of freedom settle into some low energy state that maybe learns the patterns or structure of some external force pressing on them. And the way that the parameters of a neural network move and change and interact in order to like adapt to the training procedure, which is sort of like an external stress. And they learn the image of the training data that's impressed upon them. That analogy felt interesting and appealing and worth exploring. As time's gone on and I engaged more with the literature and formed more solid ideas and talked to people, that idea has become a lot less heuristic and a lot more grounded in things. But the core feeling that this process, like learning is somehow a process by which the image of the training data is impressed upon the initially random weights of a neural network, still feels right to me. I still believe in that. And the understanding the nature of that sort of transcription feels like one way to ask the big questions of deep learning.
So tactically, how did you get started? I mean, first thing happened, you have a long late night conversation with your housemate and you're like, wow, that'd be hype. And then you wake up the next morning, like, how did you actually get into doing deep learning?
And also what initial research questions did you get interested in?
Yeah. After being set on this path, I still bounced around physics labs for a bit until talking to someone else in my cohort. I heard about this research center called the Redwood Center for Theoretical Neuroscience. There's a certain type of PI that lies at the three-way intersection between physics, neuroscience, and machine learning. There's a number of these around the country at various universities. And Berkeley's like instantiation of this archetype is Professor Mike DeWeese, who's a member of the Redwood Center. So I joined his lab early in my first year and started working with a graduate student on a project trying to understand optimization landscapes of neural networks. And that project was how I got my initial exposure to many of the big ideas. The graduate student there was, I think, a sixth year, and we only overlapped for a short while, but he was a good mentor and he helped give me the lay of the land in the current machine learning field.
Mm-hmm. After you're working on optimization landscapes, like...
Or I guess, what was that project about?
Yeah,
also,
were there any
like,
interesting...
Yeah.
Were there any interesting takeaways from that?
I took a number of takeaways from that project, both in terms of science and in terms of like how I wanted to do that science. Scientifically, the project was about finding critical points of loss surfaces. One way to understand the optimization of anything by gradient descent is to picture a surface that represents the function you're optimizing over the space of parameters you're optimizing. And imagine the process of optimization as following some downhill trajectory on this surface. And then you can imagine, like, in principle, all of the information of the optimization lies in that landscape. So if you could ask arbitrary questions about landscapes, you'd understand arbitrary answers about optimization. Now, of course, for neural networks, these landscapes are very complicated, especially if you have, millions of parameters that are all interacting in these highly nonlinear ways. The challenge, which the field was especially interested in at the time, was like, how do we understand why, despite the complexity of this landscape, we always seem to reach global minima or good solutions? And they seem to work just about equally good every time you reinitialize and run it again. There's not like huge variation between one run and the next run. And one leading theory at the time, inspired actually by an old StatMech calculation from the 90s, was that, well, actually, there are no bad local minima. That actually, despite the complexity of this loss surface, it turns out to be the case that if you're ever at a point that's a local minimum where none of its neighbors are any better than it, this point is guaranteed to be sort of good in an absolute sense. Like you don't have something like a mountain lake in the loss surface where you have a little local basin, but that's still high in altitude. It's like if the surface curves up in every direction, then you're low in absolute value or near zero.
So all local minima are global minima, or like all minima are global minima.
Yeah, exactly. There are no bad local minima.
And is that true in statistical mechanics or like in a different physical system?
Yeah. So the reason why we might think this to be true is that the simplest possible statistical physics model of a random surface exhibits this property. So that if you just take a prototypical random surface, no structure whatsoever, just a random function lying in high dimensions, it's simple for something called a Gaussian process in machine learning. Then for sort of a common class of Gaussian processes, physicists worked out a number of statistics about it and found that there are no bad local minima.
That's interesting. I feel like I saw something at NeurIPS maybe a year or two or three ago about like there's some connection between neural networks and Gaussian processes. So in a sense, like maybe that sort of almost directly applies to neural networks. I don't know the exact. There's some kind of like, oh, neural networks are Gaussian processes in some sense, but I forget the exact sense.
Yeah. Yeah, exactly. So a number of connections between Gaussian processes have been discovered in the last few years, especially related to infinite width neural networks. Now, actually, this connection came before those connections were discovered. So that's actually a slightly different statement you're referring to. Like, we want to think about the loss surface being a random function, a Gaussian process of the parameters. Right. Though there is this famous result now that for an infinite width neural network at initialization, the function value, so different object there, is the Gaussian process of the input.
Right.
So then it's true that this conjecture could apply, or this physics result could map exactly if you were optimizing the output with respect to the input.
Right.
Although in practice, you're optimizing the loss with respect to the parameters. But nonetheless, it makes heuristic sense that this conjecture might give you the right intuition. Even if it's not a good quantitative match, maybe the heuristic that complicated functions in high dimensions of no bad local minima might still map over. The reason why that might make sense is because, well, if you're at a local minimum, there are no directions that improve your loss. But if you have a million directions to choose from, odds are one of them will help you improve your loss. Until, of course, you get so low that the loss cannot be improved. And then statistics sort of forces you up. I think this is a great example of a setting where taking some intuition, especially physical intuition, from a really minimal model that captures something that you care about, in this case, random function in high dimensions, can give you a useful bit of takeaway intuition that you can then check against an actual system. And then if it matches, then you can conjecture that you've understood something. So people put this thing to the experimental test. A few big studies found that, there are no bad local minima. And they also confirmed another prediction of this model, which is that as you look at saddle points, basically, the number of upward curving directions, first, the number of downward curving directions, is a monotonic function of the absolute height. The idea here being the lower you go, the more directions curve up until you get to the bottom, and now all directions curve up.
Right.
So some high-profile studies found that this was indeed the case. But the graduate student I was working with on this project had a bone to pick with these results. It turns out we found that the algorithm people were using to find critical points wasn't finding critical points. It was finding another type of point that's also, believe it or not, a bad local minimum of the critical point finding algorithm.
What? Really?
Yeah. So even though neural networks don't have bad local minima, this critical point finding algorithm does converge to points that are not zeros of their objective. The sort of punchline result we found was just that probably no one has ever found a critical point of a large-scale deep neural network.
Like a true critical point.
Yeah, a true.
Because the critical point finding algorithms were bad.
Yeah, they were finding fake critical points.
Interesting. And so what's the value of finding critical points? Why would you want to do that?
The value is in the confirmation of this Gaussian process picture from statistical physics. It's this idea that the number of upward curving directions of critical points is a monotonic function of the value of the loss, paints a really compelling picture of the structure of the loss surface. And it's really nice for thinking about optimization behavior. So if it were true, it would be a really useful thing to know. If true, that should be a figure in every intro to machine learning textbook.
Interesting. If we were to zoom forward, knowing what you know now, how true is this? I
would say, based on our results, it seems likely that no one has the evidence to say one way or the other. I actually still think it's true. So in that case, our paper was rather methodological at the end of the day.
That makes sense.
But if I did take a fair bet, a 1-to-1 bet, I would bet it's true.
Okay. 1-to-1 odds. Got it.
That's pretty funny. I mean, that sort of work is still good to do. It's good to be correct and proper about these things. And hopefully somebody can confirm that at some point. Because knowing that it's 50-50 is important versus knowing that it's confirmed, right? 50-50 is still kind of a lot of, or some uncertainty, even 20 or 30% uncertainty.
Yeah. And if someone can confirm it robustly, then I think that's a great achievement. And it would have been good to be part of the story of getting to that point.
Totally. So you said that this work helped you understand what you wanted to work on and also how you wanted to approach the work. How did it affect that?
That work was important for me understanding what my comparative advantage was. I knew nothing about machine learning. I didn't know what a ResNet was. I had never heard of CFAR10. I didn't know any of the proper nouns or methods. My Python skills were mediocre. But where I found I contributed was in the finding of the understanding. What I found was like even the seasoned graduate student who had been working on this and related things for many years could get some value out of talking to me to try to understand at the end of the day, what is really going on? Like, why is this algorithm failing? So my contribution to our paper ended up being, after we saw these failures, I came up with a toy model. I thought of a few little low-dimensional toy functions that exhibit a not too weird structure where when you run these common algorithms on them, even though they have critical points, the algorithm converges to this other type of point that we identified. Isolating the phenomenon of interest, this failure in a toy case, let us really see what's going wrong and also like identify what type of point we were actually finding instead. Mm-hmm. This wasn't just an illustration of things we already understood. Like we understood more after we found this toy model and ended up like really influencing the framing of the paper. So the lesson I took from that was that I'm a theorist.
That's a good lesson.
Wow. That's a good thing to know early on in grad school. It's very important. Yeah.
And I think it's very true. And it taught me also the value of turning to toy models to understand phenomena in complicated, inscrutable systems. Mm-hmm. That's a lesson that I still carry with me all the time.
Mm-hmm. And so when you move forward from that project, where did you look next and what did you think next?
So next, I came across this fascinating phenomenon called mode connectivity. The nature of mode connectivity is basically like this. If I train a deep neural network twice and I find two distinct minima, surprisingly, you can find a path through parameter space that connects these two minima, and it's pretty much minimizers all the way. You don't have to climb a big hill to get from one valley to the next. You can just go around. There's a path through this high-dimensional space. And actually, these paths are really simple. You can usually find a path that only has one kink. It's just piecewise linear with two lines. And that seemed...
For all?
Piecewise linear, and it's strictly true or approximately true?
Approximately true.
Okay. Yeah. The other one was going to be a little bit just blowing my mind. All right, approximately true.
Yeah. So you can find a piecewise path where only a small fraction of samples are ever misclassified along the whole path. Mm-hmm. This was interesting to me because it seemed, the field was obsessed with this, but no one had any compelling understanding. But it seemed to me like clearly this is a result of high dimensionality, right? Just like with the fact that there are no bad local minima in high dimensions, if you have a million dimensions to choose from, probably you'll find a path from point A to point B. Mm-hmm. I started thinking about the structure of this sort of problem and like imagining the lost landscape for different models where at first you had one training point and then another point and you build up this like iterated series of constraints that constrain your allowable space you can move in. And then trying to think about, we can make some prediction about whether or not the space is connected in this mode connectivity fashion. So this led me to percolation theory. Percolation theory is another statistical mechanics model. Mm-hmm. And the type of question that it tries to ask is like, suppose I have a space that I randomly divide into passable space and impassable space. Mm-hmm. Like a classic example might be, I have a random graph and I choose some fraction p of all edges, and I can only move on those edges. Or another visual example is like, I take a random cow and I look at the fraction of white space on its side.
A very important practical problem.
Yes. Yeah. That was the inspiration of percolation theory. Percolation theory is statistical mechanics' answer to the question of like, how do we understand connectivity phenomena in random spaces? So I read a bunch of percolation theory literature and came up with a prediction about dimensionality, where like if the number of data points is, I think, much less than the number of parameters, I expect connectivity. And if it's much greater, then I don't. And I checked it. I spent the early part of the pandemic framing this question and coming up with models and reading about Gaussian processes and like checking this prediction. And it totally failed. I found like actually mode connectivity was much more robust than I thought. I couldn't find a case where I didn't see mode connectivity. Right? Even when I predicted from StatMech that I shouldn't, then I still did. So that convinced me like, okay, this like sort of isotropic random function model I had for the loss landscape maybe is missing some important structure even for a fully connected network. Right? But then I thought more about it and then realized that maybe I could co-opt my percolation theory idea to the other use case of Gaussian processes in neural networks, which is what Josh mentioned earlier, which is the fact that a neural network at initialization is sort of a Gaussian, if the function value is a Gaussian process of its input. So if we just change spaces now, maybe somehow if you talk about connectivity in input space instead of in parameter space, then maybe now these tools from percolation theory apply.
Okay, so previously you were looking at mode connectivity in parameter space, and that's where you find these distinct minima. Is that right? Like where you find that you can find a path that connects minima?
Yeah.
In parameter space. Okay, so now we're looking at input space.
Yeah. Okay, so I'm going to describe an experiment. I'm going to ask you to just give your intuitive guess for what you think would happen. Okay, so imagine I randomly initialize a deep neural network that maps input images to one of 10 classes. The input images lie in some high dimensional space, like R to the several thousand. Now, imagine I take the pre-image of a certain class. So I look at the set of all input points in inputs in image space that get mapped to a particular class, say cat. So try to picture what that set looks like in your mind. The question is, which one can test?
Before training.
This is before training, a randomly initialized net. So do you think that this set of all these points forms many distinct regions, or do you think that they're all connected into one big region?
Oh, weird. I guess my instinct is that if you have a network that maps them all to the same class, then they would all be connected into one region.
But this is a randomly initialized.
But it's randomly initialized. So I guess what does it mean for it to be connected into one region?
So the subset of the input space could either form several islands or one big ocean. The question is like, can you find a path from any point to any other point without leaving this set?
Well, since it's so high dimensional, can't you always kind of find a path to go from one place to another place without leaving that set, just because you got so much like extra variance to work with?
Exactly. It's the same intuition from before. It turns out it's extremely easy to find paths that connect any 2 points that are mapped to the same class by a neural network. This is true actually even after you train it. And the intuition is, I believe, exactly what you said, that in high dimensional spaces, connectivity is easy. Finding connections is easy.
You were co-opting percolation theory.
Yeah, okay, so it turns out percolation theory makes this prediction, but it predicts that then things are not connected if the input space is smaller dimensional than the number of classes. So if you had some hypothetical situation with a low dimensional input space, but a high number of classes, so the space is very fragmented, you can like perform this heuristic transfer of like intuition from a number of different percolation theory models to this situation, and then hypothesize that you should not see connectivity. Exploring that was the direction that this project took. I found some initially promising results, and I gave a talk to the Redwood Center about it. And then that project has been on the back burner for some time, but I've recently been working on it with another graduate student. So hopefully I'll have some publishable results to show soon enough. Or maybe it'll turn out to be wrong. I don't know.
Why does connectivity matter?
Why does connectivity matter? It's interesting in that if you could make this mapping to percolation theory, it might allow the transfer of other tools and concepts from theoretical physics. And generally, like the bridge between statistical mechanics and learning is very strong, but mostly in like, there are many paths that are very well trodden. If this worked robustly, it would like make a very strong new tie between the disciplines of sort of like a new and rather surprising type. And it's interesting for that reason. Why does it matter from a machine learning perspective? I think there's no first order reason why.
I don't know about mode connectivity for input data, like input data to output. I'm not sure. But I'm not sure if this is quite the same thing. But for the parameter space, I remember seeing something, I think last year, that was about you can kind of permute the weights and change things around to get from like one trained network to another trained network. And that was actually pretty interesting because maybe it was even at NeurIPS this year where like you can find ways of taking almost anything that was trained and permuting it to this like more canonical form, which is really interesting because then like it's just so obnoxious to deal with all these weights because then you can't do like hyper networks and things because to do a hyper network, you're like, oh, the weights are all over the place. This is stupid. But if you had a canonical form, now you could think about this thing as like you're just outputting this one thing as opposed to outputting this whole set of millions of different like numbers, right? So that's like a much, much easier thing to learn.
So actually, I guess Ken Jun's question was, why does connectivity matter? And I think it doesn't matter so much in the input space. That's maybe the case where it's most easily understood. In weight space, it matters because it tells us about the structure of the minimizers of the neural network. And mode connectivity has remained a sort of mainstay object of interest in optimization studies of deep neural nets. People have found it has sort of connections to feature learning where like either training at late times or training in the NTK regime, or training in what's called the neural tangent kernel regime at infinite width, you define mode connectivity. That tells you about sort of the structure of your problem. The problem space is simple. But if early in training, if you sort of branch off your optimization early in training, then the two solutions aren't connected by as simple a path as they would have been otherwise, which tells you ended up in a different region. It's not just a really basic basin.
Interesting. Okay, so you explored this, and then where did your research interest evolve from there?
So this was about the time when I started getting into the theory of infinite width neural networks. At first glance, the idea of an infinite width neural network as a useful object of study sounds insane. And why should this be a reasonable limit to take? Like why, if we want to understand a neural network, which like obviously has to be finite to do anything useful, could we hope to learn anything by just making something infinite? Like that especially is baffling from the viewpoint of classical statistics, where you hope to find a parsimonious model. You want to like wield Occam's razor like a sword. So it seems baffling at first that this should be useful, but it turns out actually a number of like breakthrough results in the, especially, around the early part of my PhD, found that some really like non-trivial, insightful behavior emerges when you take this infinite width limit. And they have the flavor of statistical mechanics, thermodynamic limits. And actually many of the authors in these works were trained as physicists. The analogy there is like, okay, imagine I have a bunch of particles bouncing around in a box, and I want to understand what they do. Like, how fast do they go for a certain amount of energy? How hard are they pressing on the walls? What's their distribution? Maybe they have some interaction with each other as well and some internal degrees of freedom. Well, okay, if I have 100 particles in a little box that are bouncing around, it's going to be very annoying to characterize their behavior. Like they'll interact in complicated ways. Like 100 is a lot of degrees of freedom to understand from theory, at least. But if I have infinitely many particles in a box, then it suddenly becomes simple. I have a gas or a fluid. And this is how like the ideal gas law is derived. Like P equals nRT is derived in the limit of infinitely many particles in the box. The number of particles turns out to be close enough to infinite that this is like a pretty good, useful approximation. And actually it kicks in earlier than you'd expect. The same thing is true for neural networks, where taking the infinite width limit gives you nice, simple equations you can study. And also when you compare to a network that is with 1,000, oftentimes you see pretty fair agreement, like qualitative agreement, like very often, and quantitative agreement sometimes. So the study of infinite width is a very valuable foothold for people who are trying to understand how to think about neural networks.
When you say there's qualitative agreement between like 1,000 wide network versus an infinite width network, what kind of qualitative agreement?
Yeah. So to answer that, I think we need to step back and try to think about what it is we're trying to do when we understand neural networks. This is a deep question that often gets swept under the rug and I think merits more discussion. What are we trying to do here? Are we trying to be able to predict the movement of every parameter? Do we need a model for our data? But like, what are we trying to understand and what does it mean to understand? So one answer to this is in the process of training and using neural networks, we'll, come across a number of like clear qualitative phenomena that are repeatable across like problems and domains and networks. And then we might want to come up with like good explanations for these. So an example of such a phenomenon is training on noise takes longer than training on data. If I train a network on a data set and I look at how its loss drops and then train the same network with the same procedure on that data, but with noisy labels, the loss drops slower. It takes longer to fit the noise. That phenomenon is captured perfectly by this infinite width limit. If you train a network at infinite width, it still does this. Now, the curves might not exactly overlap, but you train noise, or it takes longer to train on noise. And what's even better is because infinite width, the network takes such a simple analytical form, you can understand why that's true. Through the study of infinite width, like people can now explain to the satisfaction of even a mathematician, why this was harder to do. And it has to do with poor alignment of something called the neural tangent kernel that emerges at infinite with the random function relative to the initial clean function.
And so there's like better alignment with non-random data.
Yes, which also happens to be a way to look at why machine learning generalizes at all. In the case of infinite width, if the neural tangent kernel only has trivial alignment, like just chance alignment with the target function of the data, it won't generalize on it. But in practice, we see very good alignment between this kernel object and then the target function. And there's been a lot of work, including from like me and my co-authors more recently, trying to go from the target function and its alignment with the kernels to understand generalization that now can really like paint this picture quite clearly, that in the infinite width limit, generalization is like very clearly quantitatively given by some function of the alignment between the kernel and the target function. And then a question you could ask is like, why do convolutional networks do better than fully connected networks on image data? Well, it turns out their kernels have better alignment with the image data.
Oh, interesting. Okay, so if I'm understanding kernels properly, is it that each network architecture has a kind of like a form of kernel? Like, even though they might have different, I guess I imagine that if you so each architecture has a different form of kernel.
Yeah, that's right. You could imagine that each class of architecture, like convolutional, fully connected, transformer, recurrent, has a different class of kernel function. A kernel is sort of like a similarity function over the data space that tells you how similar the model believes at like a priori two examples are. Sort of encodes the inductive bias or the prior beliefs of the network. And yeah, like all convolutional networks will have kernels of a similar class at infinite width. The detailed structure will depend on the depth and the stride and the convolution size and all of these other hyperparameters. But like pretty robustly, kernel functions of the class convolutional have better alignment with data than kernel functions of the class fully connected, at least so long as the data is image data.
And so in theory, you could take a convolutional kernel and then kind of like try it on different types of data. And maybe you could find image data that didn't align well with it, or you could find its alignment with other data.
Yeah, so there turn out to be computational bottlenecks doing that, but yes, if I handed you a new type of data you had never seen before, and I asked you to choose what type of architecture would perform best on it, and you weren't allowed to train any neural networks or run any algorithms or make any predictions, just looking at computing this kernel and looking at an alignment score would give you a pretty good idea of what model class would perform best. Now, the thing that I was really interested in doing for a while was, so now building off that idea, there was something that I got interested in for a time around the middle of my Ph.D., which was the question of like, can we use this as a design principle to discover new architectures? Like, if you hand me a problem I've never seen before, can I somehow measure the problem, design a new kernel without even worrying about neural networks, and then once I find the good kernel, convert that into a network and then train it? With the hope being that you could do better than you could with this like blind, brute force, inscrutable process of neural architecture search that's the default today. So this led to a paper that we called Reverse Engineering the Neural Tangent Kernel. And there, for fully connected networks, we sort of made this mapping where you can hand me a kernel and I can hand you back fully connected neural network that has this kernel at infinite or moderately large width, which like completes a step in this sort of proposed pipeline for neural architecture search or for neural network design you could imagine building.
That's the method for going from the
kernel to network.
Yeah,
kernel to network. But presumably you also want a way to go from
network to kernel
or data to kernel or something like that.
Yeah. Okay. So what's already known, what was figured out first is how to go from network to kernel. What we'd like to do is to go from data to kernel and then kernel to network. Our work sort of builds the first bridge for the second step of that. You know, we put the arrow from kernel to network. We still need an arrow from data to kernel. And the kernels have been around for a good 20 some odd years. People have proposals for ways to do that, but none that could discover something like convolutions from first principles. So like that arrow is still very much open. And I think it'll have to wait for a better structure. Drawing that arrow requires some insight into the structure of natural data. And the reason why I've moved away from this for now is because I feel like we don't have the understanding yet. And it'd be more interesting to try to build understanding of the structure of data in order to unlock this potential process of going straight from data to architecture in a principled fashion without a lot of blind trial and error.
So for reverse engineering the neurotangent kernel, given a kernel, you give me a fully connected network. Is there anything weird from this process of generating fully connected networks? Are there like properties of the network? Like, is the network harder to train or easier to train? Or is there anything interesting in this?
One interesting surprise was that with a few technical caveats, pretty much any kernel you want for a fully connected network, you can achieve it with only one hidden layer. So the original title for this paper was actually On the Power of Shallow Learning.
That's a great title.
We found that basically any kernel that could have belonged to any deep, fully connected network, you can achieve in just one hidden layer, with the technical caveat of normalized data, which turns out not to matter that much in practice. So this let us do this interesting experiment where we took a classic tabular data set from the UCI suite, and we trained a 4 hidden layer ReLU network on it. Anyway, we plotted its loss and accuracy curves over time, and it did pretty well. That was the best step. And then we plot a 1 hidden layer ReLU network on the same task, and its curves are different. It doesn't do as well. But then we extract the kernel from the 4 hidden layer network at infinite width, which is something you can do analytically. We use the ideas from our paper to translate this into a single hidden layer network. It turns out it's just a normal network, but it has a sort of peculiar activation function that we had to design. And we trained that on the same problem. And it matches the 4 hidden layer ReLU net exactly.
Wow.
So like, if you only look at ReLU, it seems like depth matters. But actually, if you're allowed to choose an activation function, then you find that you can choose one that worked as well as the ReLU net. So somehow, at least as insofar as the kernel regime goes, there was no advantage to depth. It wasn't actually buying you anything. And this is the sort of result that I really like because it is like a very clear signal. Like, it's not like performance here was better than performance there. It's like these curves lie on top of each other, and it's made from first principles theory. At the end of this experiment, we felt like we had actually understood something. So
it's super cool.
Yeah, it's really interesting. So in theory, like, we should be able to take any fully connected network and collapse it into a single layer network.
Yeah. Okay, so
there's one thing missing though.
Yes. So the important caveat to that is that it's something you do before training. The exact statement is, if you had an infinitely wide neural network, a fully connected net, and actually making a fully connected net wider usually makes it better. So it's not a performance caveat. And you train that, then that would work the same as using our method to generate a different fully connected network with just one layer, and then training that on the same data, with the asterisk that the data has to be normalized. Like, it turns out for our technique to work, like, every input vector has to have the same norm as every other input vector. And it turns out that enforcing that, though, doesn't really affect performance much. Even if you don't enforce it, actually, we still see good agreement. So that it's like mostly a theoretical caveat to get the theorem to work. The thing you can't do is take a trained network and compress it. Although, even though that would matter more practically, I think this is more interesting theoretically. Like, I think as much understanding of neural networks should be a priori understanding, pre-hoc understanding, not post-hoc understanding. So it's good if we can say stuff before training occurs.
Yeah, that makes sense. Is the single layer network easier to train, or does it have any other benefits due to being single layer?
Well, it is smaller in terms of parameter count.
That's true.
So especially if you want it to be wide, as soon as you have more than one hidden layer, you have these big width times width dimension matrices. But if you only have a single hidden layer, then your scaling is actually, it's only proportional to width, because you only have one wide layer. So we found that you actually do perform better, like at fixed parameter count.
I see. Yeah. Given fixed parameter count, you perform better. That makes sense.
So you imagine in principle, like in a very memory constrained environment, for example, on a cell phone or in the 70s, then you could like get some benefit out of doing this. Although I wouldn't want to overstate it, and I think mostly it's cool and not useful yet.
Yeah, it's an interesting theoretical result. Would you guess that anything like this applies to other architectures that are not fully connected networks?
I don't think that convolutional networks can be collapsed to a single layer like mechanics networks can. But I do think that the deeper idea of reverse engineering kernels is powerful and probably holds across architectures. So the central message isn't really like, here's the particular theorem for fully connected networks. So the central message is, let's think about the inductive bias of architectures in kernel space directly and see if we can do our design work in kernel space instead of in a parameter space. And it turns out, that I think very likely will work for other architectures and is interesting.
That's really interesting. I think particularly interesting that I guess like I assumed that depth was what allowed for a lot of the learning, kind of like the learning capacity. But in a fully connected network, it sounds like actually you can like smush a lot of that into the activation function. It turns out that like learning capacity doesn't come from depth.
Yeah, a lot of prominent theorists also have that intuition. And there are results even for fully connected networks that say when you have deep networks, you get all these benefits. You get like exponential expressivity. There are functions you could express in a deep network with a handful of parameters that you need like many, many more parameters, maybe exponentially more parameters to get with only one hidden layer. And those results are true. But of course, like real data isn't these special functions that are designed to be hard to get in a single layer. So this is a lesson that can be taken from this, that not every clear, provable difference between two architecture classes will matter when it comes to training and performance on real data.
And the intuition there is like real data has some regularities, and those regularities make it so that you don't end up having to learn. Yeah, never mind. I get it.
Yeah.
Okay.
Actually, one reason why this is true is that these works, like prior works that showed that deep networks can express many more things than shallow networks, didn't show that they will actually learn them if in practice when trained on data. There's this notion of expressivity, which asks, all right, for a given network with a given number of parameters and a given configuration, what functions can it possibly represent? But like, it doesn't matter if a network can express something if it won't learn it given a reason. And that's an enormous difference.
So it could be that like deep networks can express these really complicated functions, but in fact, it does not need to learn these really complicated functions. It just needs to learn more simple functions that maybe shallow networks can also learn.
Yeah, or actually, like a more pessimistic view is that neither the deep nor the shallow net will learn a complicated adversarial function. The classic example is like the XOR function. This is a famous example of a function that's really easy to specify, but really hard to learn with a neural net. The function there is like, okay, I give you a bit string, zeros and ones, and you have to tell me, I want you to give me a 1 if the sum of the bit string is odd, and a -1 if the sum of the bit string is even. That's extremely simple to state, much simpler than classify cats versus dogs. But fully connected networks don't learn it. It's a famous example of something that is much harder to learn than to express.
Earlier, you were talking about being that there is not just qualitative agreement sometimes, but also quantitative agreement sometimes between these like infinite width networks and actually like normal trained networks. What kind of quantitative agreement?
So you see good quantitative agreement when the network is in sort of the same regime as its infinite width counterpart. And what that means is like when the dynamical conditions that the infinite width version satisfies are also satisfied at finite width. So that means finite networks behave like their infinite width counterparts more when width is large, of course, but also it turns out when the data set is small or when they're trained for few steps. But like once you have a practical neural network trained on a big data set to convergence, usually then the quantitative agreement fades. Although people have shown interestingly that if you take the neural tangent kernel of a network after training, then the real neural network after training looks a lot as if it had always had its final neural tangent kernel. So like you don't have to worry so much about the evolution over time so much as where it ended up only. But I think that's a little too technical to
I see. So kind of the intuition there would be like, okay, if you try to trace the neural tangent kernel like every step during training, then it does not follow quantitatively. But if you take the neural tangent kernel after training, then it actually maps out pretty well.
Yeah. But your question was like, when does a network look like it's infinite width counterpart? And I think in that case, it's not fair to say that it looks like it's infinite width counterpart.
Yeah, that makes sense.
It's mostly in settings that are like a medium degree of unrealistic when they really give a good quantitative match. Although, and this has led to a lot of opposition to the adoption of the NTK, the neural intelligent kernel, as a concept, especially among more empirically minded folks. Because like, well, real neural networks aren't in this regime. Why should we care? It's the question about infinite width all over again. The reason why we should, in my view, is that, well, we didn't understand anything before, so we might as well squeeze this lemon for all it's worth. And quantitative agreement in sort of toy regimes and qualitative agreement in more realistic regimes is pretty good for a theoretical toy model of things.
I see. So your argument against people who say it's not useful would be or like not interesting, not useful to study for real world neural networks. Your argument would be something like, actually, toy models generally don't necessarily quantitatively agree, except in toy regimes. Actually, it's great to have a model that does get good agreement qualitatively.
Yeah, that's part of it. I think it is conceivable that eventually we'll have a toy model that captures the learning of interesting features, like what's called feature learning, which is the main thing the NTK is known to not do. But absent that, there's a whole breadth of questions, like at least 5 or 6 different subfields of deep learning theory where you can get some understanding by looking at kernel methods, then transfers heuristically over to deep neural networks. So I think people who point out its limitations are correct in noting limitations, and like people are right to look for things beyond it. But at the same time, I think there's a surprising amount we can learn just from studying kernels.
So you have another really interesting paper, and it's on eigenlearning. Can you explain how it came about and the interestingness, importance of it?
Yeah, sure. The theory of machine learning algorithms is often divided into 2 main facets. There's questions of sort of training and dynamics. Things like optimization, behavior, and convergence lie in this camp. On the other side is generalization, which says, independent of how you got to the final solution, how well does it do? How well does it generalize from your training data to your test data? Because ultimately, that's what you want from any machine learning algorithm. So in the summer of 2021, I was thinking a lot about how to think about the generalization of kernel methods, including wide neural networks and the neural tangent kernel and so on. And sort of out of nowhere, this like really gifted student named Maddie Dickens, who transfers into our group from condensed matter physics. She was sort of later in her PhD and had like all these really powerful tools from statistical physics at her disposal. And we started working together. She was interested in thinking about the generalization of machine learning methods. And pretty quickly, we started noticing things about the generalization of kernel regression. Now, we were not super aware. We later found out that there's an enormous body of literature on this that I've since gone back and integrated. But at the time, we were sort of working blind from square one and trying to sort out the generalization of, or trying to figure out how to think about the generalization of kernel regression, equivalent to wide neural networks. And the thing that we noticed fairly quickly was that, well, for one, it makes sense to think of the problem in a certain eigenbasis of the kernel. So if your data is drawn from some distribution, you can take any operator, including a kernel operator, and diagonalize it over this distribution. You can find eigenfunctions that have corresponding eigenvalues, just like you can find eigenvectors and eigenvalues of a matrix in an intro linear algebra course. And it turns out that these eigenfunctions and their corresponding eigenvalues encode the inductive bias, the learning behavior of a particular kernel. It turns out kernels more easily, more readily learn functions with higher eigenvalue and are more hesitant, they require more data to learn functions with lower eigenvalue. So we set about trying to turn this qualitative observation into a sort of quantitative theory. And our first breakthrough on the project came when Maddie and I were working at a chalkboard, and she writes down this peculiar quantity that's sort of like the mean squared error, but it's linear instead of quadratic. It's just the expectation of the product of the true function and the predicted function, as opposed to the expectation of the squared difference. This was weird. And at first I was sort of dismissive of it, but she was like convinced that this was an important quantity somehow, but couldn't articulate it. And we thought about it for a while. And then I became convinced that this was somehow a conserved quantity. So from playing around with it a bit, I had this intuition that somehow when you change your kernel, you improve this learnability quantity on some functions and you make it worse on other functions. But I felt like there should be a sort of conservation law, a zero-sum game at play here. And we talked about this, and I had my intuition and she did formal math, and we couldn't make them connect. And then the next day, within minutes of each other, we each independently proved this conservation law.
Okay.
So we find that this learnability quantity is indeed conserved.
So can you explain, first for our audience, what is an eigenfunction and what does an eigenfunction mean and what does an eigenvalue mean? And then what is learnability?
So what are these eigenfunctions and eigenvalues over this data set? How are they defined? You can define them as a certain limit. So first, imagine I sample n points from my data distribution. And then I construct an n by n kernel matrix. So a kernel function just takes in two inputs and sort of tells you how similar they are. It's just a generalization of a dot product. So if I have a data set of n points, n samples, I can construct an n by n kernel matrix, also called a gram matrix, where entry ij is just kernel evaluated on xi and xj. Now, this is a matrix. It's going to be a symmetric matrix because the kernel is a symmetric function. And so it has orthogonal eigenvectors and corresponding eigenvalues.
Just of the matrix. Is this a regular matrix? Or just regular eigen?
Yeah, it's just a matrix.
Cool.
It turns out the eigenvalues of a kernel matrix will always be positive, or at least non-negative. And now imagine instead of giving n randomly sampled points from our distribution, I take n to be infinite. So it includes every possible point you could ever choose from your input space.
Mm-hmm.
Okay. Well, now this eigenvector, it's a vector with infinitely many components, and each component corresponds to one of the inputs. So you can imagine it's like a function, right? What is a function but a vector with infinitely many components, each of which corresponds to one input x? And treating that vector as a function, this is now an eigenfunction. And the eigenvalues are the same as they were before. And what this means sort of intuitively is like an eigenfunction of a kernel that has high eigenvalue is a function such that similar points, according to the kernel, which is a similarity function, are assigned similar function values. So, for example, oftentimes the highest eigenvalue function is simply the constant function, which makes sense because all of points are assigned similar values because they're always the same value. And working your way down, this all depends on the kernel itself. But for most common kernels, including neural tangent kernels, more slowly varying functions have higher eigenvalue. For example, if you're on some nice domain like a sphere or something, usually for a rotation invariant kernel, the eigenfunctions are just what's called the spherical harmonics. And these harmonics sort of can be grouped into the constant function and then sort of functions that vary slowly and functions that vary a little bit faster and so on in these sort of like levels. And the eigenvalue just sort of gets lower and lower as you get to these more and more complicated functions. So this has been a big discovery of the machine learning theory community over the last few years, how to understand the sort of simplicity bias of kernel methods towards high eigenvalue eigenfunctions, which happen to be sort of smooth.
Got it.
So another way of saying it is almost like, if you want to learn classifier and you just classify everything as the same, that's the simplest. And you might actually be like right more often than not because your data is skewed. But then as you learn like your more coarse things, you can actually like just learn a few very coarse things are enough for you to get pretty far in terms of your learning.
When you say more readily learn, like what is needed to like, it requires more data to learn functions that have lower eigenvalue, which means functions that are more complex. Does it mean that it will learn the simple function first and then it will slowly like complexify to fit the new data?
Yes, that's exactly what I mean. Turns out that this bias occurs both in training time and in number of samples. At a given number of samples, you'll only learn something like the top order number of samples eigenfunctions. If your function has a component that's lower than that, your kernel is blind to it. And also early in training time, you won't have had time to resolve these lower functions. So until you train for long enough, even if you have enough data, you'll be blind to these lower eigen. The main contribution of our work, which we ended up calling the eigen-learning framework because it describes the learning of kernel methods in this sort of like eigen sense, is that this quantity called learnability acts as a natural currency for the inductive bias of a given kernel on data distribution. This conservation law tells you that the kernel only has n units of learnability total, where n is the number of training samples. And the kernel then must allocate these n units among its eigenmodes. And each eigenmode must get between 0 and 1 unit of learnability. modes with higher eigenvalue get more learnability according to a simple formula. So the picture at the end of the day is sort of like your kernel has this budget of inductive bias, n units of learnability, and it allocates them out disproportionately to the top eigenmodes. And you can understand a whole variety of other interesting things you might care about, such as, importantly, the mean squared error of your predictor, entirely in terms of how much learnability is allocated to each eigenmode.
Interesting.
So the picture we derive here is sort of a two-part framework, where first you ask, how does your kernel allocate learnability to eigenmodes? And this is like a simple process and very easy and tangible to think about. And then once you know how learnability is allocated to your eigenmodes, you can take these mode-wise learnabilities and plug them into a fairly simple formula and get out estimators for things like mean squared error, which is the most important. And also things we show like the smoothness of the function, sort of the mean squared gradient instead of just the mean squared error.
Interesting.
Yeah.
So would it be accurate to say something like, if you use this eigenlearning framework, then you just given the data samples and some process, some like algorithm for figuring out how the kernel allocates ability to eigenmodes, you can now compute estimators for MSE and the smoothness of the function without having to do any training?
Yeah, that's exactly right. So the catch is that the formula that we derive requires sort of global information. We use the terminology of another work that calls this predictor the omniscient risk predictor, because you sort of need like the full eigeninformation, more than you could possibly glean from any finite sample. It turns out you can do a pretty good job of estimating this from a large finite sample. But like, formally speaking, what we derive is sort of a theoretical tool that lets you say, given some structure on your data, how will you generalize when you train your algorithm? And yeah, like given this knowledge, you don't actually need to train the algorithm. Like computing the predictions of these equations is more or less instantaneous and much faster than actually running kernel regression. But even better than being fast, it's simple and analytically tractable. So both in the eigenlearning paper and in follow-ups, I've like used these equations to derive useful properties of the generalization of model kernel regression systems in a way that like would have just been either really complicated or impossible without this tool.
That's really interesting. Okay, so this seems like magical. Like, you have a tool where, given data and some model, you don't need to train the model. You can just compute what the model is going to learn, and then end up knowing what kind of final. You jump to the end without any training.
Well, you have the model at the end. You know how good the performance will be.
What
you can actually classify it. Well, that's still useful.
Okay. So I guess, when can I use this, and where does it not work? I guess I could, in theory, use this in order to say, okay, this data is not very good because the model is going to end up with high mean squared error, and so we should get more data of higher quality. That I could see that as like as a way to use this. But where do you feel like we can and can't use this?
Yeah. In principle, you could use it if you were trying out, say, a family of kernels and you were trying to find which worked the best, or if you were trying to optimize something like the ridge parameter in kernel ridge regression. These equations let you, for example, try a bunch of ridge parameters very fast, and sort of optimize over that hyperparameter without having to actually invert a new matrix and run kernel regression again each time. The catch, I guess, is that computing these equations for the first time on real data is sort of as expensive as just running the algorithm to begin with. And so the value is really in the understanding. Like, these equations are very simple and interpretable and can give you insight into why the kernel performed well and perhaps how it might work better, or why one kernel worked better than another at a given set or a given problem.
I guess tell me if this is wrong, but my understanding is, I guess you need to reach like this very expensive calculation for each kernel, or is it really for the data they expensive for? Like, can you try out lots of different kernels?
The answer is basically yes. Like, unless you have a very special family of kernel, then you do sort of need to rethink the calculation from scratch. The case when you don't is if your data distribution has some nice symmetry properties, for example, like perhaps you know the eigenbasis analytically, and you also know that your kernel respects those symmetry properties too. Mm-hmm. For example, like rotation invariant kernels, pretty generic family, on a rotation invariant domain, you can sort of understand analytically. And for this reason, a lot of work on kernel regression studies exactly that family.
Mm-hmm. Yeah, I guess that's too bad that you can't just, try out lots of kernels really quickly, because that'd be a nice place to be. I mean, that'll only be half of the way, but if you could do that, and you could, I guess you need two more things. If you could try out the kernels really quickly, and if you could figure out the kernel for a given neural network architecture, I think maybe that one's doable. And if you knew how to bridge between kernel learning and feature learning, then you might be able to estimate how well a neural network architecture will perform on data without training.
Yeah, exactly. This is exactly the tenuous bridge between ideas that I had in my head when I was doing this work and doing the reverse engineering, the NTK work. You can sort of imagine this new paradigm of deep learning where deep learning architectures connect theoretically to the kernel. You can understand the kernel's behavior on the data. And then if you can just draw the arrow back from the kernel to the architecture, which is what I was trying to do with reverse engineering the NTK, then you can start to think about how you could start from your data, try surrogates for architectures very fast, and then sort of translate them with some principled theoretical methodology back into a good neural architecture. So this was the dream. And I think probably while this requires much more exploration to be made viable, I think pieces like this probably can ultimately be made to work. But the gap between getting things to work with fully connected networks and simple domains to things like transformers is pretty big. I've since turned towards other things, but I think it's still a sort of compelling vision of a way that we could put a principled theoretical scaffolding to the process of deep learning and neural architecture search. And I certainly still have it in mind and compare new ideas to it.
That makes sense.
Yeah,
it's really
cool.
interesting.
We can certainly donate that idea to research. If someone else wants to go the rest of the way, it'd be interesting to see it for sure.
Yeah.
I wholeheartedly approve of that.
Thanks for listening to the Generally Intelligent podcast. If you like this, please consider giving us a rating and leaving a review on Apple Podcast. On Twitter, I'm @Kanjun, Kanjun, and our lab is @GenIntelligent. Until next time.